Okay, today's lesson will be on acceleration. Acceleration occurs if we have a change in speed and or direction. So this means a change in velocity over a period of time. For example, if you had a plane that started at some initial time with some initial velocity and ended at a different time and a different velocity, you would have acceleration. Remember, this is indicated by a curved line in a displacement time graph. And I'll show you more about that later. The reason it's curved is because you're covering more and more distance every unit of time because you're going faster and faster. All right, let's use this illustration to come up with an equation for acceleration. Once again, you have some initial time and some initial velocity, a final time, and a final velocity. And all acceleration actually means is how that velocity changes over time. So the average acceleration would therefore be change in velocity over change in time. We can use this for an example. Here's a plane that's speeding up. It has an initial velocity of 0, a final velocity of 260 kilometers per hour. We started the clock at 0, and we ended the clock at 29 seconds. So what is the acceleration? The final speed minus the initial speed over the final time minus the initial time comes out to be 9 kilometers per hour per second. What does this actually mean? That the speed of the plane is increasing by 9 kilometers per hour every single second. I'll show you that in the next illustration. We started at 0. We have an acceleration of 9 kilometers per hour per second. So after 1 second, you're at 9 kilometers per hour. After 2, you're at 18. But acceleration doesn't mean that you have to speed up all the time. Sometimes you could be slowing down. So here's an example of a drag race car that started at 28 meters per second and ended at 13 after it opened up its power chute. The time doesn't always have to start at 0 as indicated here. The time initial is 9 seconds. The time final is 12 seconds. Putting the numbers in, we have the final velocity minus the initial over the final time minus the initial time comes up to be negative 5 meters per second squared. What does the negative indicate? That it's in the opposite direction we called positive. In other words, the velocity was positive to the right, but the acceleration is to the left, negative. All right, let's see what this means. All right, we started at 28 meters per second at time 0. Actually, time 9 seconds, but you get the idea. After 1 second goes by, we're down to 23 meters per second. After 2 seconds go by, we're down to 18. In other words, the acceleration was in the opposite direction of the velocity. All right, now I want to look at a velocity time graph and see how that's related to an acceleration time graph and also to a displacement time graph. We know the slope of a graph is rise over run. So what is rising in this case? Velocity. What is running in this case? Time. So therefore, the slope of a velocity time graph must be acceleration. All right, let's talk about the area underneath a velocity time graph. All right, we have a curve. I'm using the generic term curve. In this case, it happens to be a line, but it works for any shape curve. It happens to be a triangle, so I'm going to use the equation 1/2 the base times the height. In this case, the base is 2 seconds and the height is 2 meters per second. Notice that if I look at the units, seconds cancel out, and I'm left in 2 meters. So what does this indicate? Well, it indicates that the area underneath the velocity time graph gives you displacement. And if I did the same thing for 4 seconds and 4 meters per second, it comes out to a displacement of 8 meters. And at 6 seconds, it would be 18 meters. I can keep on going on and doing this every 2 seconds. Ooh, I don't know why I did that. And this idea will work for any shape. Once again, I use the idea of a triangle in this case because that's what it was, but it really works for any shape curve. Okay, here's the original data we had on the last slide of time and velocities. We were able to calculate the displacements by taking the area underneath the velocity time graph. And here what I did is I took those displacements from the area underneath the velocity time graph and I plotted them. And it does indeed create a curved line as we anticipated it. Okay, now I'm going to show you a short little video that's going to show the relationship between velocity time, distance time, there's displacement time, and acceleration time graphs.
A ball rolling down a long incline will be used to show how position, velocity, and acceleration of the ball change as it moves down the incline. 5 lights arranged along the length of the track flash simultaneously once per second. As the ball rolls down, it is directly above each of the lights just as they flash. This gives us a record of the positions of the ball at 1-second intervals. This is how far the ball traveled in the first second. This is how far the ball traveled in the first 2 seconds, 3 seconds, 4 seconds. We will move this distance up to a graph to keep track of position versus time. Does position change linearly over time? Next, we will graph the average velocity of the ball during 5 different intervals to see how velocity varies as the ball rolls down the incline. The ball moved this far during the first second. It moved this far during the next second, this far during the third second, the fourth second. This gives us a graph of the velocity of the ball over time. Does velocity increase linearly? Now we will graph the changes in velocity versus time by graphing the differences in successive velocities. What does this tell us about the acceleration of the ball? The acceleration is constant.
All right, now we're going to have a quick little check for understanding. We have 3 graphs here: displacement, time, velocity time, acceleration time. And there's no acceleration. In other words, it's constant velocity. What I want to know is what does the displacement time graph look like, velocity time graph look like, and the acceleration time graph. All right, and I would also like to try the same thing with constant acceleration. So what would the acceleration time graph look like, the velocity time graph look like, and the displacement time graph? So why don't you take a moment, make those sketches, see what they look like, and then we'll go over the answer. So pause the video now, okay? All right, we're back. Hopefully this is what you got. This is with constant velocity. Constant velocity would mean that you would be covering the same distance every unit of time, or same displacement. So you would go up the same amount every unit of time. So your speed is constant, so it will stay the same amount every unit of time. So it would be a straight horizontal line. And if it's constant velocity, therefore there'd be no acceleration. Now I couldn't show exactly the line exactly at 0 because it would just overlay it, so I showed it next to it. All right, and constant acceleration. What do these graphs look like? Hopefully you got this. Well, constant acceleration would be a straight line, straight horizontal line. Now it could be positive or negative. In this case I happen to show positive. It could be a constant acceleration in the negative direction by being below the origin. And if the acceleration is constant, then the velocity would increase by the same amount every unit of time. It would go up by the same amount every unit of time. And if it's constant acceleration, you're going faster and faster and faster and faster. So you're covering more and more distance. All right, let's talk about the area underneath curves. we have an acceleration time graph. The area underneath it would be velocity, because the area would be the acceleration times time, or meters per second squared times seconds, would give you meters per second, which is velocity. The area underneath the velocity time graph would be velocity times time, or meters per second times seconds will end up being meters. And there's the displacement time graph. So let's think about this. If we take the area underneath this guy, we can get this one. Take the area underneath this one, you can get this one. If you take the slope of this guy, you get this. Take the slope of this, you get this. Now this slope, you would have to take instantaneous slopes because it's changing over time. Okay? All right, now I'm going to do one of those check for understandings again. I'm going to give you 4 questions. And I'm going to pause the video and ask you to answer them. So at this point, pause the video. And we're back. So the slope of a displacement time graph is velocity, because you would be taking displacement over time, which is rise over run. You would end up with velocity. Took the area underneath the velocity time graph, you would get displacement, because it would be velocity times time would be displacement. And the slope of a velocity time graph is acceleration, because it would be rise over run, or velocity over time, acceleration. The area underneath an acceleration time graph is velocity.